Hi everyone. In this video we're going to discuss the calculus of polar coordinates. And now that we're experts with parametric equations, we'll quickly see that the techniques are one and the same. So let's begin. Let's recall what polar coordinates are. We know that x is equal to r times cosine of theta. We know that y is equal to r times the sine of theta. And we know that if r is equal to some function of theta, plugging that in quickly gives us that x is equal to f of theta times cosine of theta, y is equal to f of theta times the sine of theta, where theta is between two values, maybe a and b, that sweep out the portion of the function that we care about. Could be negative infinity to infinity, I really don't care. And now that we have a parametric equation for any polar curve here, we can do calculus, right? And before we begin doing calculus, let me just give you a disclaimer. This video does assume that we are pretty fluent with our knowledge of polar coordinates and polar functions and polar graphs. So if any of that is not familiar or it's not as familiar as you would like, please reach out and ask any questions that you have, and I'm happy to help in any way that I can. All right, so now we have a nice fun parametrization with a smiley face under it, right? These make us very happy because we know exactly how to compute dy dx, which gives us the slope of any line tangent to hopefully this polar curve, which is weird. We can find equations of tangent lines to polar curves now. We know that dy dx will in fact be dy d theta. Theta is our parameter up here. It could be t, but I like theta. Divided by dx d theta. How do we find dy d theta? It's going to be the derivative of f of theta times sine of theta with respect to theta. And so by doing the product rule, we see that it's quickly f of theta times cosine of theta plus f prime of theta times the sine of theta. Divided by dx d theta is going to be f of theta times negative sine of theta plus f prime of theta times cosine of theta. And it looks pretty terrible, but that's okay. But this is dy dx. This does give you an equation to compute the slope of any line tangent to this polar graph. As always, because the setup is the same now that we are in parametric equation land, right? When will we have vertical tangent lines? Those correspond, of course, to whenever dx d theta is equal to 0. When will we have horizontal tangent lines? Those, of course, correspond to whenever dy d theta is 0, just like parametric equations. The moral of the story is that all of our knowledge here will follow, all of the calculus that we'll develop here follows from our knowledge of parametric equations, which is super helpful. All right, so let's do something fun. Maybe I'll flip the paper. Okay. Let's compute arc length of a polar curve. And we're experts on arc length with parametric equations after the last video, right? We recall that the arc length of a curve expressed as a parametric equation is the integral from a to b of the square root of the derivative squared of x prime squared plus y prime squared, right? So in this case it's dx d theta squared plus dy d theta squared d theta. And we could leave it here and we could just use the parametric equation and compute this each and every time, and it will work, and that's totally fine. There's a slick little formula that pops out, though, if we do the computation, so we'll do that. But you don't really need it if you don't want to memorize it. It's totally fine. Let's just write on the paper here. that x is equal to f of theta times cosine of theta, y is equal to f of theta times the sine of theta. Let's recall that. And so let's plug in here. We get the integral from a to b of, well, what's dx d theta? We wrote on the previous page that this is going to be f of theta times negative sine theta plus f prime of theta times cosine of theta, quantity squared, plus f of theta times cosine theta plus f prime of theta times the sine of theta, I'm running out of room here, all squared, and a big, giant, friendly square root on top with a d theta shoved at the end. Yeah? And I know that this looks even worse, but it's not. So what I want you guys to do now, expand this out. So distribute the square here, distribute the square here. Use the fact that sine squared theta plus cosine squared theta is 1, and you'll see a nice reduction. Pause the video, give it a shot. So we hopefully see that we have the integral from a to b of the square root of f of theta squared plus f prime of theta squared d theta. And that's super nice. Maybe there's a happy face. All right. Let's do something different. Let's compute the area of regions enclosed by polar functions. Suppose we have a polar curve. Maybe it's wiggly. Yeah, here's our polar curve. And suppose we want to find the area of the region enclosed between two values of theta, maybe theta 1 and some other value, theta 2. How do we find the area of this region? Well, we're in calculus, right? What's the mantra of calculus? Anytime you want to do anything in calculus, the answer invariably is chop it up into small bits, get your information on the small bits, and then add everything together, right? So in this case, what are our small bits going to be? We're going to chop up this polar region. We're going to pierce everything radially and chop up our region into tiny little sectors. And we know that for this polar region, we can approximate it with the sector of a circle. The angle of this sector of our circle is maybe delta theta sub I, where we've partitioned the interval from theta 1 to theta 2. And let's recall now that the area of a sector of a circle is 1/2 times theta r squared. Yeah? Well, what's r in this case? R is equal to f of theta, right? So I know that we can approximate the area of this little piece of my region here by instead approximating it with the area of this sector, where the radius of my sector is given by f evaluated at some point theta I star on this interval. Yeah? So now what can we do? We know that the area of my entire region that I want is approximately equal to if we add up the areas of these individual little sectors of circles. Individual areas of these sectors of circles. So that's the sum of all of my sectors, so from 1 to n, of 1/2. So what's the area of the sector? It's 1/2 times theta. What's theta here? It's delta theta sub I times the distance from the origin squared. And what's the distance from the origin squared here? It's f of theta sub I star squared. But we're in calculus, right? This is just if we have finitely many sectors that we've chopped this region into. Let's take now a limit as n approaches infinity. And all of a sudden we have a Riemann sum. So the area becomes exactly equal to the integral from theta 1 to theta 2 of 1/2 f of theta quantity squared, and our delta theta sub I becomes d theta. Or if you prefer, and it'll make it look more like this up here, you could write this as integral from theta 1 to theta 2 of 1/2 r squared d theta. Yeah. And it looks very similar to this guy, except for theta, what's theta now? It's just itty-bitty pieces of theta. Yeah. And whenever you add up all those individual sectors, you do in fact recover the area of the entire region. Let's do some examples. Find the area enclosed by one petal of the curve r equals sine of 3 theta. Find the area enclosed by one petal of the curve r equals sine of 3 theta. So what's step one to every problem? Let's draw a picture. If we don't have a picture, it makes it kind of intractable. Let's recall what this function looks like. I know that 3 is an odd number, so it will have 3 petals. Remember, if it's an even number, the number of petals double. And I know I'm going to have y-axis symmetry because this is sine of 3 theta. Cosine of theta has x-axis symmetry. And if we recall the graph here, it starts at r equals 0. And it will go out, come back to r equals 0, and then down, and then back out again. And then from here it cycles. And all of these petals go out the same distance. I just can't draw. So pretend that all these petals are kind of the same, right? They're all the same area. So how can we find the area enclosed by one of these petals? Let's say this one. Well, we know what r is. We know that the area is equal to the 1/2 the integral from theta 1 to theta 2 of r squared d theta. We know what r is, so we're almost done, right? All that we need now is theta 1 and theta 2. All that we need to find are theta 1 and theta 2. So I want you to pause the video. Try to find the values of theta 1 and theta 2. The strategy that I recommend is finding the value where you have r equals 0, and then find the next subsequent value where you're back to r equals 0, and that will define one petal. Give it a shot. Pause the video. All right, so let's set sine of 3 theta equal to 0. Yeah, because this is r. We want to find where r is 0 to see where we cross through the origin. Well, where does sine of stuff equal to 0? I know that that's going to be where 3 theta is equal to pi n, where n is an element of the integers. So that means that r is equal to 0 whenever theta is pi over 3 times n, where n is an element of the integers. So all that we need to do now is find 2 consecutive values of theta. So let's do 1/2 integral from 0 to pi over 3 of sine squared of 3 theta d theta. And it's kind of easy. Let's talk a little bit more about how we can see the bounds of integration visually. Visually, I can see that I start sweeping my angle theta at theta equals 0. And then I come back and I stop sweeping at about theta equals pi over 3. So whenever I start at theta equals 0, I go out, 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 come back, I'm at theta equals pi over 3. So we can also see visually that it is from 0 to pi over 3, and this little strategy here can help us as a tool that we can use to actually get the values exactly, so that we don't just have to rely on eyeballing it. All right, so how do we integrate this function? We, of course, need to use the double angle identity, so let's do that here. If you're not 100% sure with this, please, please, please pause the video, do this integration for yourself. Make sure that you're 100% comfortable with it. So we know that this is going to become 1/2 integral from 0 to pi over 3 of 1/2 minus 1/2 cosine of 6 theta d theta, because it's twice 3 theta, right? Which is going to be equal to 1/4 times theta minus 1/6. This 1/4, I just factored out the 1/2 here. I hope that's not confusing. Sine of 6 theta. And let's evaluate this from 0 to pi over 3. If I plug in pi over 3, that's pi over 3. Sine of 2 pi is 0. Similarly, as we saw before, sine of 0 is also 0. So we're left with just pi over 12. And that is not so bad. Oops, not a pi, but I want a smiley face. All right, let's do another problem. Example. Let's find the area of the region inside the large loop of the function r equals 1 plus 2 cosine theta, but outside the smaller loop. Find the area of the region inside the large loop of this curve, but outside the smaller loop that it has. Let's recall how to graph this together. If you know how to graph this already, or if you've seen this graph before, please pause the video, try to graph this yourself, right? If you don't know how to graph this, let's do it together first. Let's plot some points together. If theta is equal to 0, 1 plus 2 is equal to 3. So if theta equals 0, r is equal to 3. So I'm 3 units away from the origin. Whenever theta is equal to pi over 6, say, cosine of pi over 6 is root 3 over 2. So I'm 1 plus square root of 3 units away from the origin, which is just a little bit shy of 3, but inclined at an angle of pi over 6. At pi over 3, along the line pi over 3 here, cosine of pi over 3 is 1/2. 1 plus 1 is 2. So I'm closer to the origin now. At pi over 2, so straight up here, cosine of pi over 2 is 0. So we're up by 1. Yeah. At 2 pi over 3, cosine of 2 pi over 3 is negative 1/2. But if we have negative 1/2, 2 times negative 1/2 is negative 1, plus 1 is 0. So we're back at the origin. So from 0 to 2 pi over 3, our shape looks something like this, it turns out. Let's plug in 5 pi over 6, and 5 pi over 6 is this angle back here, right? If we plug in 5 pi over 6 together, cosine of 5 pi over 6 is negative root 3 over 2. But whenever we plug that in, that becomes 1 minus the square root of 3, which is negative. So rather than actually being along this ray, it goes in the opposite direction at a distance of 1 minus square root of 3, which is somewhere maybe here. If we plug in pi, Cosine of pi is -1. 1 minus 2 is -1. So rather than being along this direction, we have to go the other direction. And so from here, it comes back out, loops down, and then it keeps looping on and makes this type of shape. Yeah? I think it looks a little bit like a butt. And so really, we want to find the area of this region. How do we do this? I want you now to pause the video. Try to figure out, now that we have a nice picture, try to find the area of the dashed region here. Give it a shot. All right, so we know that the area is going to be equal to the area of the outer region minus the area of the inner region, right? That's our knowledge from calculus. So we need to find the area, first and foremost, of this outer loop, and then we're going to subtract the area that we've over-counted in the middle. So we need to find what separates them. We know, let's trace it together with our pencils. We're going to start here at 3, it goes up. We hit r equals 0. Then we're on the inner loop. We hit r equals 0. Now we're back on the outer loop. So as we saw in the previous example, all of this hinges on where does r equal 0. So let's set r equal, which is 2 cosine theta, and let's set that equal to 0 and solve. We see that this is whenever cosine of theta is -1/2, which occurs whenever theta is equal to 2 pi over 3 and 4 pi over 3. These are the solutions in one revolution, right? But we saw that 2 pi over 3 to 4 pi over 3, that was actually the inner loop, right? We started on the inner loop whenever we were between 2 pi over 3 and 4 pi over 3. We were on the outer loop at theta equals 0. So how do we actually define the outer loop? We need another point, don't we? What about -2 pi over 3? So what's the area of the outer region? It's 1/2 -2 pi over 3 to 2 pi over 3 of 1 plus 2 cosine theta squared d theta. Here's my outer area. But we need to subtract 1/2 the integral from 2 pi over 3 to 4 pi over 3. Of the same curve. So pause the video, work out these integrals. It's the same double angle identity that we've used a few times now, so give it a shot yourself. All right, and hopefully we see that the answer is 3√3 plus pi, unless I've made a mistake, which could definitely happen. But the setup is really the most important part here. This is easy integration, just maybe a little tedious. The setup is very important. So make sure that you are totally okay with setting up this problem. Let's do another problem. Find the area of the region inside r equals to 4 times the sine of 2 theta, and outside the circle with radius 2. Yeah. Let's recall together what the graph of 4 sine of 2 theta looks like, in case we're shaky on our graphs. 2 is an even number, so I know that this is actually going to have 4 petals. And it looks something like this. And as I'm drawing it, this is as theta progresses from 0 to 2 pi. Oh, and my petals are terrible. But pretend they're all the same length because I am a terrible artist. And again, it starts at theta equals 0. Here's pi over 2. Here's pi. Here's 3 pi over 2. And we're back to 2 pi. And I know that the maximum extent here is going to be at pi over 4. What's sine of pi over 4? Or sorry, what's 2 times pi over 4 is pi over 2. Sine of pi over 2 is 1. So the maximum extent is 4. So we end up 4 units away from the origin there. So our circle of radius 2 will lie inside of this. Something like this maybe. And we want to find the region, or the area of the region inside the rows and outside the circle. So we really want to find this dashed region here. And remember, there's actually 4 regions. Yeah? So pause the video, see if you can figure this out yourself. Okay, so we know that we can take this dashed region and just multiply it by 4 to get the answer that we're looking for, right? So it's going to be 4 times 1/2 the integral from theta 1 to theta 2. Who knows what those are yet? And how are we going to find the area of just this dashed region here? The idea is to pierce the region radially. So let's pierce this region, starting at the origin. We're going to pierce it kind of where I drew that purple line earlier. Pierce it through the origin. And the integral, just like we saw with areas in single variable calculus, it was top minus bottom or right minus left. Here we subtract outer area minus inner area. Yeah? So what is the outer function? What's the outer radius? So we know that we're going to have, let's do it kind of symbolically here. It's going to be the outer radius squared minus the inner radius squared. And we're going to integrate that d theta, right? So 4 times 1/2 is 2. Integral. What's my outer radius? What's the outer function that we have? It's going to be 4 times the sine of 2 theta, right? Squared. Minus. What's my inner radius? The inner radius is, of course, 2, because that's the function r equals 2. D theta. Now all that we're left to do is find the values of theta 1 and theta 2. And unfortunately now we can't use the r equals 0 trick anymore. We really want to find the points of intersection, right? We want to find where this piercing is valid, where we pierce and we stay in the region that we're looking for. Outside of those points of intersection, we're no longer in the region that we care about. So we really need to find the points of intersection that define this region. So we need to set 4 sine of 2 theta equal to 2, because these are the equations of the two curves. 4 sine 2 theta and 2. Solving this, we see that we need to solve sine of 2 theta equals to 1/2. And the two values in this case that will work are theta equals pi over 6. 2 theta equals pi over 6. And theta equals to 5 pi over 6. Yeah? Dividing by 2, we have theta equals pi over 12, and theta equals 5 pi over 12. And now, pause the video, make sure that you're okay with the integration. It shouldn't be too bad. And I hope you see that the answer was, hopefully, 4 times the square root of 3 plus 8 pi over 3, unless I made a mistake. All right, guys, I thank so much for your attention today. I hope that this video helps. If you have any questions about the content of the video, please never hesitate to reach out and ask me any questions that you have. And I look forward to seeing you in the next video. Thanks so much.